Or hey friends, just trying to supplement since our class didn't work today over the internet issues. So this is more so for my second hour class, but we're working on our writing quadratics functions and modeling notes and homework during class today. And we got through some of this stuff, but if you're just watching this to watch it, all this stuff on this first page was done in the other video for your virtual Wednesday by Mr. K. But where we started in class was just trying to summarize like, hey, what am I supposed to use what form of a quadratic? So this page here, I'll just let you pause and kind of copy on your own. If you want to add this, there's no space for this in your notes. So what we were doing in class was just taking out a separate sheet of paper. But for each of the three forms, you want to kind of have some indicators as to like what form or like when should I use it. And obviously like with something like vertex form, you should use it when you have the vertex. But like when we start to apply things to real life models, it's never going to say this is the vertex. So we would look for words like maximums or minimums. Now, when you're writing in this form, the vertex helps you find H and K. So you would need to find the letter A by also knowing one other piece of information. You should use intercept form when you have the x-intercepts. But again, when it comes to like word problems, they're not going to say, and this is the x-intercept. When it comes to word problems, we'd want to identify the dependent value as some form of 0. So like the dependent value could really change, like the height was 0, or the amount that you've earned was nothing. So an indicator that you have the intercepts is when the dependent values are 0. And then same thing with like our vertex form. The intercepts help us find P and Q, but would normally need another piece of information to help us find A. And then standard form really honestly is just kind of like your last option. And I wrote down, you should use standard form when you can't use one of the other forms. Because again, these other forms are more visual. If I know the vertex, for instance, is something like 1, 6, in the equation, I see those numbers. I see the 1 and I see the 6. Same thing with the intercept form. If it's written with a minus sign, the x-intercepts I specifically see, maybe the signs are opposite. I see them in the equation. But the standard form equation really doesn't give us anything just by looking at it. Like, yeah, we can see that that c-intercept, or the y-intercept, excuse me. But that's not super informative, just that one y-intercept. We still wouldn't know how to find A and B. So this can kind of direct your work as to like, what form am I supposed to use? So with that, this is just a good resource when we're practicing with quadratic models. What we were supposed to cover in class today was starting with something like number 3. And this one's not an application yet, but we're given 3 points. We want to write a quadratic model for them. So we can see here is like, well, what model should I use? Well, this is not an intercept because none of the outputs are 0. So it's not the x-intercepts. We don't have a y-intercept, and I have no way of knowing if any of those are the vertex. So again, I should use standard form when I don't have the vertex or the x-intercepts. Now, the way that we're going to handle it is we need to write an equation that looks like this. R should be in the form y equals ax squared plus bx plus c. Now, what we need to do is we need to find a, b, and c. Those are the letters that we'd put in an equation, right? So if there's 3 letters or 3 unknowns, that means we must have 3 equations. And the clue to this is if I look at it the way it's written now, there's actually 5 letters there. There's A, B, and C, and X and Y. I can't write 5 equations. So what we should notice is we're going to plug these points in to come up with a system of equations. So for instance, the y value will be 4 if the x value was -1. So if I plugged in -1 for x, that would just be 1 times a. And then if I plugged in -1 for x, that'd be negative b, which I can just write as minus b. And then if I plugged in -1 for x, that wouldn't change the value of c, so I'd just say plus c. Right, so we used this unique fact to come up with this piece of information. This is one relationship between A, B, and C. So we continue that process. If I plug in 2 for x, so if I plug in 2 for all of those x's, it's guaranteed that the y value is -5. So 2 squared would have been 4, so 4a plus 2b. And then this term of c doesn't depend on x, so it's always just c. But again, we used this point, we plugged in x and y, so now this equation only has 3 unknowns. Continue that process for the last point, 4, 9. I just want to use a different color. So 4, 9 has an x and a y pair. So I will get the output of 9 if you substituted x as 4. So a times 16 would have been 16a. B times 4 is 4b. And again, that value of c doesn't have an x term in it. So by using those 3 points, we now have a system of equations. And with these systems of equations, we can definitely solve them by hand using elimination or substitution, whatever one you would want. But what we'll say moving forward, unless it specifically tells you to use like a method like substitution or elimination, you can go ahead and use your graphing calculator. What I mean by that is just simply write a system or a matrix equation. So we know, just like a refresher there, if I want to turn this into a matrix multiplication problem, our first matrix are the coefficients. So 1a minus 1b plus 1c. So those coefficients are 1, -1, and 1. The coefficients of the green equation are 4, 2, and 1, 16a, 4b, and 1c. Then we always multiply by our variable matrix next. It's going to make myself some space. Well, apparently it doesn't want me to make that smaller. So again, after the coefficients, we multiply them by the variables. We're looking for a, b, and c. And that should give us our answers. I'm just abbreviating those. So the answers to those equations were 4, -5, and 9. And then again, we would just use your graphing calculator. So if this was matrix A, you enter that into your graphing calculator. I'm just going to symbolically call this matrix X, and then we'll call this matrix B. And we know by definition that if I wanted to isolate this matrix, what are the contents of that matrix, which would tell me what A, B, and C were, I can multiply on the left side by the inverse of A. And again, matrix multiplication isn't commutative, meaning the order matters. So I multiplied on the left. So I have to multiply it by the left on the other side too. So in other words, our matrix X will be given by the inverse of A times matrix B. And again, you're simply just doing that on your calculator. And just to save time then, I'm not going to show you that on the calculator because we already know how to do matrix multiplication on our calculator. But matrix X, when you use your calculator, the contents of that matrix are 2, -5, and -3. So those are the values of A, B, and C. So our final answer then is, what is that quadratic model? Well, we figured out A was 2, B was -5, and C was -3. And that would be the final answer to this question. All right, so now we can start to apply that idea. So here, this is something without context. Let's put it into context of a real life situation. So in this example, we're working as an actuary for a fender bender insurance company. So we're working on evaluating risk. So your company plans to offer a senior citizen accident policy. So we must predict the likelihood of an accident as a function of the driver's age. So that step right there, as a function of the driver's age, that helps us set up our X and our Y's. In other words, what's independent and what's dependent. Because we learned up here that if I know what X and Y are, I can plug things in and I can make this system of equations. So what it's telling me is if I knew the person's age, I'd be able to plug that into my little function calculator and it would give me something about likelihood. So in other words, age is the input value and inputs are X's. So we know that just in general, for ordered pairs, the age would come first, and then something about accidents would come after that. Because again, the number of accidents depends on the age. So you can see that we have 3 ordered pairs then. We have 20, 440. We have 30, 280. And then the last one is 40, 200. Now, what we know, as it says here, we know that the number of accidents should reach a minimum and then go up again, right? As I start driving, my likelihood of accidents is really high. As I get better with driving, I get better, and I should have less accidents. And then eventually, the accident likeliness comes up as I start to maybe age or something like that. So we're going to use a quadratic model. Now, when we're going through the quadratic model, we want to think about, well, which form should I use, right? Which form would be the best? And what we're noticing here is we don't have a vertex. We don't know what the max and the minimum was. None of the ordered pairs had 0 as their dependent values. So we have to use standard form then. It's going to be the most efficient route for us. So what we should then do is kind of remind ourselves of standard form. We want it to look like y equals ax squared plus bx plus c. So then we're able to write our system of equations, right? If we plugged in 20, the answer should have been 440. If we plugged in 20, 20 squared, so it'd be 400a plus 20b plus c. Move on to the next ordered pair. If I plugged in 30, I would get 280 as an output. So 30 squared, 30 times b, and then c. And the last ordered pair was if I plug in 200, I will get out, or sorry, if I plug in 40, I get 200 out. So 1600 would be x squared plus 40b plus c. So then once we're there, here we're going to go ahead and turn this into a system of or a product of matrices. So we put the coefficients, multiply them by the variables, and that should give us the answers to those equations. Right? The answers in order were 440, 280, and 200. Now at this point, I would just ask that you pause, go into your calculator, and solve this matrix equation, right? Find the inverse of that first matrix and use that inverse. So now that you've paused the video and you've solved the contents of that matrix using your calculator, we'll see that the contents of that matrix were 0.4, negative 36, and 1,000. So then our final answer for our equation is y equals 0.4x squared minus 36x plus 1,000. Now, all you do after that, this is our equation. And then just for a little bit of ease, instead of calling it y equals, y is just a function of x, so I'm just going to turn that into function notation. Because all they want us to do now is just use that model. So who's safer, a 16 or a 70-year-old? Well, again, it's important to know what x and y were. 16 was an input. So if I plugged 16 into my function, and you'd use your calculator to do that, it comes out to be 526. Again, when I look at this piece of information, 70, I know that age is an input, so I want to plug that age into my equation. So I'm going to plug in 70 into my function, and when we do that, we get 440. So if they asked us who is safer, the 70-year-olds are safer because they have less accidents in general. Now the next question is, what age is the absolute safest? Well, if we think about working with our quadratics, we know what this quadratic function looks like, right? Just by looking at a, we can see it's a positive number. So our function is going to look something like this. And we know that this axis is age, and this other one is like accidents. So if I want the safest, I would want the least number of accidents. So in other words, we're looking for the vertex. And if we have standard form, we know the vertex is always the opposite of b divided by 2 times a. And that will give us, when you plug that in, the number 45. So that's an age at which it happens, 45 years. That's the age, that's the safest. But they also want to know how many accidents is that. So if I want to know the y value of the vertex, right, I have to take that answer and plug it into my equation, right? And I'm just using f of x instead of y because it's easier to show you that I'm plugging something in. And I believe when you do that, then you get 190, and that label is accidents per 100 million kilometers. Now, if we move on to the last one here, it's asking us, your company decides that we're only going to insure drivers up to the age where the accident rate reaches 830. So again, let's think about this little picture here. We know that we have some sort of U-shaped graph, and we know that the safest drivers happen right here at 45. And we know that number was 190. So what they're saying then is like, we're cool with up to 830. So like somewhere we know that like that's the output we're looking for. So they want us to know what is the domain of that function. So like, let's think about what we're doing here. So we want to find when our driver's accident risk reaches 830. So then we know we'd want the output to be 830. And then when we're working with quadratics, we know that we want them equal to 0 in order to solve for these things, like using the quadratic formula or factoring. Now, I do want to remind you of something like factoring works really well, and in our problems, we might try to facilitate factoring. Remember, you can use the discriminant to tell you if it's even going to factor. Remember the discriminant b squared minus 4ac. So b squared minus 4 times a times c. That number 1024, just seeing if I can take the square root of that. It's a perfect square. So if your discriminant is a perfect square, you will be able to factor it. So I'm going to factor this one. And when we're doing problems like this in our class, you kind of see that once we factor out the GCF of 0.4, and you can use your calculator to help with the division and the multiplication. Kind of brings up another important point. I'm wondering like, hey, this is a leading coefficient of 1. So I'm wondering if there's numbers that multiply to 425 and add to negative 90. What I would recommend with those is just check every factor pair. So we know that the way that we check factor pairs, sorry, this is my free app here. Just gotta wait for my calculator to come back. The way that we check to see if a number is a factor is divide, right? So like 425 is divisible by 1. So 1 and 425 do multiply to 425, but they're never going to add to 90. So I'd keep checking one number at a time. 2 wasn't a factor. 3 wasn't a factor. 4 is not a factor. But 5 is. I know that 5 times 85 is 425, and 5 and 85 can definitely make a negative 90. So I know I found my numbers of negative 5 and negative 90. So I can factor this, 0.4. X minus 90, 85, sorry, not 90, that's my fault. That was my fault. 85. That's just what I said before. And then X minus 5. So then in other words, like this is our function. So what would be like an appropriate domain for our function here? So when I'm thinking about this, or if I'm going to decide like, hey, what driver should I insure? What's an appropriate domain? Remember, domain is just all the X values that we could plug in here. So if we know that this X value right here, 5 is one of the answers that gives us that 830, and then 85 is the other one that gives us that answer. The only numbers that we'd want to plug in for X then would be between 5 and 85. But there's one little thing here that X is an age, and there's no way our company is going to insure a 5-year-old. So I have to be 16 to be insured anyway, and 16-year-olds are somewhere down here, so they're under that threshold. So anywhere between 16 to 85 would be an appropriate domain for this function, because those are the ages that would guarantee you're under that limit. All right, so at this point then, it's just kind of a random grab bag of stuff here. So I'm just gonna do a few examples if you feel like you need them. They do match explicitly with your homework. So a farmer builds a rectangular pen to hold her pigs using the side of a barn as one side of the pen. So I'm just gonna label like a barn in red. So here's our barn. And then we're gonna have this fence. That's a rectangle. What we know is that she has 68 feet of fence to make the 3 sides, right? Because one of the sides is the barn. They want X to represent one of the equal sides of a rectangle. So if we only have 3 sides, we know that these 2 sides must have been the same. So if I only have 68 total feet, I've already used X of it here and X of it here. So I had 68 to begin with, but I took away 2 X's. So we can see like our fence here is X wide, or X tall, if you will, and 68 minus whatever is left over there. So they want us to write an equation for the area of the pen. Well, we know area, right? The area is going to take X as an input, because if I know what X is, I can plug that in and find the area. So the area is the length times the width. So X times 68 minus 2X. There's no need to distribute that, but I guess if you wanted to see it in standard form, we could write that too. But I dislike standard form a little bit because it doesn't really tell me too much information. Now it says, what is a suitable domain for this function? And sketch a graph of the function using the domain. So the idea here is we're thinking about like, well, what could I measure as the side length for my fence? Well, obviously the smallest number that would represent a side length would be 0, right? But the next thing is I only have a certain amount of fence, right? So if I think about what's the total amount of fence I could use, right? So we're saying is the area is 0 if I just lay all of my fence right here, right? In other words, if I don't put anything up or down, my area is going to be nothing. But what I hope we kind of like see is like, as I start to make that bigger, right? As I start to get taller, there's going to be a point where it becomes so tall and so skinny that it's not even a fence anymore, right? It's just going to be like a line. It's not going to be a rectangular pen. It would more so be so skinny it just looks like a line. And then there's no area for my pig to go in. So I'm really wondering, like, when would my area be nothing, right? And another thing we can think about is we know this is going to be a parabola that looks like this. So I know I'd get no area if x was 0. And then when would this factor be equal to 0? Well, if each of the x's were 34, there'd be nothing left for that upper part of the fence. So this would be equal when x is 34. So the domain for my function would make sense to go from 0 to 34. Because when I think about my picture of that, if this is 0 and this is 34, if I don't put any width to my pen, there's no area. But then eventually, if I put all of that fencing, 34 here and 34 there, it's not a pen anymore. Like they're going to get out. So I wouldn't want to do that. So I'd want to go something a little bit less than that, because as long as it's a little bit less, I have enough to finish the pen. So it says, what are the dimensions that give the maximum area of this pen? Well, what's nice about this is we have some information. Like this is the 0.00. And then if I plug in 34, we know that was the number that also made it 0. Now there's two things I'd ask you to think about this is, first of all, when we look at a parabola, we know the facts of it, that the vertex is halfway between the x-intercepts. So what number is halfway between 0 and 34? Well, we can take the average, right? 0 plus 34 divided by 2 is 17. So halfway between them is 17. Now that's just the x value. Or again, you could use that fancy formula. We have standard form, negative b over 2a. The opposite of b over 2 times a will give you the same thing. So if we want to know the dimensions, we know x is 17. So if this was x by 68 minus 2x, well, our dimensions would be 17. And then if we plugged in 68 minus 34, which is twice of 17, that gives us 34. So what is the maximum area then? Well, if I know the dimensions, I simply would plug in the x value of the dimensions to get the area. And when you do that, I think it comes out to 578. And since we're multiplying feet by feet, we get feet squared. Again, just another example. So Mia's in a hot air balloon flying at a height of 90 feet. Zach's on the ground directly below and throws a ball into the air with a velocity, releases it at above 4 feet above the ground. Will the ball reach the balloon? So like in other words, if we can kind of draw a little picture here, there's this balloon that's kind of like here, let's say, and we're going to throw a ball and we're going to wonder, is it ever going to hit that balloon or not? It's kind of like the general idea. And what it's saying is we're throwing a ball and it's starting at 4 feet in the air because like we're not throwing it from the ground, we're standing. So we're going to throw this ball up in the air. It's going to come back down and we're going to wonder if it's going to hit this hot air balloon. Like if the hot air balloon is there, it's going to hit it. If the hot air balloon is up here, it's not going to hit it. So we're wondering if you can throw it high enough to hit the air balloon. And then it kind of gives us this like overall understanding. We need to use this formula that gives the height of the ball at any time. We've got to fill in some values here. H is the height. V is the initial velocity. H is the initial height. And I think this is the initial height is what we mean too. Or sorry, no. H is the overall height. This is supposed to say H sub 0 right there for the initial height. So the height of the ball at any certain time is negative 16 t squared plus its velocity. Now its velocity is given to us as 70 feet per second, so 70 feet every second, and its initial height was 4. So what they want us to wonder is, will the ball reach the balloon? So if the balloon is 90 feet in the air, I'm wondering if our equation would ever be true. Is there a value of t that I can plug in that would make the output equal 90? If there is, then my ball hits the balloon. If there isn't, then it doesn't. So it asks us to do this in 2 different ways. The first way is the easiest, which is the maximum. So way number 1, we know that if we're throwing a ball, the maximum is the vertex. So what is the maximum of this equation? Well, right, if I want to solve this, sorry, not this equation, but like I'll write this equation down here. This is the height of my equation. This equation, negative 16 t squared plus 70t plus 4. So that picture I drew over there, I want to know, is this point have a height of 90 or less? So the maximum is the vertex. So the vertex, and this time it's t, the opposite of b, all divided by 2 times a. And we're using our calculator here, so I'm just going to take mine out because I don't think we get super nice numbers. So negative 70 divided by 2 times negative 16 gives us 2.1875. So I'm just going to store that to my calculator as x, so I know that it's 2.1875. And then if I know what that x value is, or in this case the t value, I'd have to plug that in. So the height at that number, I'm just going to use my calculator. Since I already have it as x, I can just type my equation in. Negative 16, whoops. So negative 16x squared plus 70x plus 4. So that tells me the height at that point is 80.56. So no, that means the maximum height of the ball, which takes about 2.1 seconds, is only 80 feet. So the hot air balloon is up here at 90. So that means no, it will not intersect. The other way that we could do it, remember I said do it 2 ways, is we could just go and solve this equation. So I'm going to do that just up here in the margin, right? Rather than knowing anything about the maximums or the minimums of my function, if I want to know when this equation is true, I can just solve this quadratic equation, right? We've learned that in Algebra 1, but to solve a quadratic equation, we get it equal to 0. So I've subtracted 90 from both sides. And then we just use the quadratic formula. So the value of t, because we're solving for t, is the opposite of b plus or minus the square root of b squared minus 4ac. So 70 squared minus 4 times a times c, all divided by 2 times a. Now when we are solving for this, what we're going to realize here is that under the square root, we get a negative number. So we know that if there's a negative under the square root, there are no real solutions for t. So in other words, there is no value of t that I could plug into my equation that would give me an answer of 90. So with this, there's no solution. So we kind of see that same thing.